This is my fork that I just found. Atoms. They come in different sizes and different colors. Wait, okay, not different colors. An official dress shirt, and I did wear my camouflage because this is my favorite color, and they're shorts. Welcome to day one of distance learning. Yeah, I've been doing this for quite a while. We have actually had the capacity to do this for like a dozen years, but there are a lot of your teachers that are not used to this kind of thing. So please bear with us as we get into this. Looks like we'll be in this for the long haul. So here I am by the creek. This is one of my favorite spaces. Bring the kids up here. There's a whole lot more water than usual. Wander up the creek, have a great time. But I have brought an official dress shirt, and I did wear my camouflage because this is my favorite color, and they're shorts. First, this is unprecedented. This is not anything that we have ever seen before. We've not ever, in anyone's experience, really seen the shutdown of our entire economy to keep people from dying from this new virus. So we're trying to figure this stuff out. Governments at all levels are trying to do this. Read the Constitution. It's a pretty good thing to help you understand how this is all going. Lots of people have lost their jobs. Sorry if you're one of those families that is experiencing significant loss. There's a major drop in the stock market, which is affecting people's retirement plans, college plans. All these things are up in the air. Now, within the next few weeks and months, we're going to be opening all this stuff back up, and hopefully we have a strong enough economy, and the world has a strong enough economy, we can get this thing back going. But we'll figure this thing out. It's new to everybody. Today's topic is we're gonna start electrostatics. Static electricity. You rub yourself on your seat in your car, you get out and you touch the metal on the outside, and zap! You're inside your house, you're shuffling along in your little slippers, you touch the doorknob and zap! That kind of static electricity is what we're gonna start with today. But the one thing that you're gonna miss, that you're not gonna get from the book, that you're not going to really understand to really get you started, and the one thing that has consistently, over my almost 30 years of teaching, gotten students tripped up is that they apparently think like Aristotle even after taking chemistry class. You see a fork and you think, oh, that fork has fork atoms in it. And you see, hold on, where's my knife? What a knife. You see a knife and you think, oh, well, there's some plastic atoms and there's some metal atoms. No, you cannot look around at your world and believe that these things are made of fork atoms and human atoms and tree atoms. You can't think like that. You have to think differently. This is my fork that I just found. The dirt that you see there, it's made of atoms and molecules. The metal is made of atoms and molecules. The fingers are made of atoms and molecules. This thing right here made all of atoms and molecules. And this is the one thing that you will forget, and this is the one thing that will lead to your downfall in the study of static electricity. Those rocks, atoms and molecules. The water, atoms and molecules. It's not pure water, and none of these things is pure. The metal in this blade that you can barely see because of that ceramic coating it has on it. I think it's ceramic. The metal on that blade, that is not pure steel. It's not pure anything. All these things are alloy. There are lots of mixes, lots of different molecules that are put together. Ooh, starfrit. So keep that in mind. Atoms and molecules. Atoms. They come in different sizes and different colors. Wait, okay, not different colors, because there is not color at that level. But if you take your fingernail, take a look at your fingernail, got the little fingernail, right? The thickness of it, divided into like 1,000,000 parts, that's still bigger than an atom. And sometimes atoms can get stuck together. They form bonds of various types, and sometimes they form chains. But the one thing you have to remember is that this, what you think of perhaps as a solid atom, is not as solid as you think. Rutherford's gold foil scattering experiment told us that that vast majority of that thing, almost everything here, there's nothing in there. There's absolutely nothing in there. And the only reason that my hand can't pass through this ball is because there are electrons on the outside of this. Electrons on the outside of this repel the electrons on the outside of this, and that's what you have to keep in mind. Inside this, which represents an atom, and that which represents an atom, and those which represent atoms, inside those you have a nucleus, a tiny little nucleus made of protons and neutrons. but we're not going to pay attention to those. The one thing we're to pay attention to is the electrons on the outside. It's the electrons, people. The electrons are moving. The electrons are negative. So let's go back over atomic theory. This is the atom, and you've made this particular kind of thing with Skittles a bunch of times before in the past. We're going to use the green to represent the protons, the yellow to represent the neutrons, and the pink to represent the electrons. And again, we are particularly interested, pretty much exclusively interested in the electrons. And in here, this is the nucleus. The scale in this model is completely wrong, so ignore it. The nucleus is like a golf ball or a baseball in the middle of a huge baseball stadium like PNC Park downtown, and then the atom is the whole stadium. So we have 1, 2, 3, 4, 5, 6, 7, 8 protons. That 8 protons determines how many electrons you need to give you a neutral atom. And then 1, 2, 3, 4, 5, 6, 7 neutrons. In this particular isotope of, wait, what is 8 protons? Atomic number 8. That would be oxygen. So this is oxygen. Oxygen has 8 protons. This one has 7 neutrons. There are 15 total particles, nucleons in here, and that 15 total particles gives you oxygen 15. Not the most common isotope of oxygen, but one of them. Different numbers of neutrons gives you a different isotope. So we have 1, 2, 2 in that first level. This is not really how things work. They're not really planets. They're not even really particles most of the time. Anyway, we super simplify this so we can get it. In this first orbital, we have 2 electrons, and then 1, 2, 3, 4, 5, 6 in the second orbital for a total of 8 electrons for a neutral atom. If this is sharing electrons, then it doesn't always have 8. If it is, well, this is what this oxygen does, but if you have an ionic bond, which you generally don't have with oxygen, then you would lose one of these things. Now, in charging, for electrostatics, the only thing we're dealing with is these electrons on the outside. You can take electrons away and you can add electrons to objects. So if you think of this as, well, all the objects are made of these atoms. And if you take one of these things and it gets kicked out, it has less negative. And if you have less negative, or the thing has less negative, electrons have been taken from you, then you're positive. Because what's fixed? The number of protons is fixed. That is neutral. And then if you continue adding other electrons, oh, that is negative. So adding electrons makes things negative. Taking electrons away makes things positive. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.